All right, so in this example, we're going to look at centroids in the case where the area that we're interested in is the area between two curves rather than the area under one curve and above the x-axis. So let's say that in general you have the function f of x as your curve on the top and g of x as your curve on the bottom. In order to find the centroid of your new region here, we are now going to be thinking about the vertical distance from bottom to top here instead of the simple height from the x-axis to the top of the function. And so every time that we would normally have seen an f of x or in our integral, we're actually going to have the difference f of x minus g of x to get the height of the function. So for example, in our x bar equation here, normally we would just have the integral of x times f of x dx, but now we have the integral of x times f of x minus g of x. So we get x, the horizontal distance, times f of x minus g of x, which is the vertical distance there. That's how we're going to figure out the x bar value. Then for y bar, again, very similar to the original formula, normally we would have just had the integral of 1/2 times f of x, the quantity squared, but now we also have to subtract g of x, the quantity squared. So again, upper minus lower there. And it's important when we think about this formula that we remember that the squaring comes first before the subtraction here. So we're not subtracting the functions and then squaring, we are actually squaring first and then subtracting. You can see some details about how this is worked up in the textbook, but this is the basic idea here. Okay. So now let's actually use this to solve a problem. Let's find the center of mass of a shape bounded between two curves. So in this case, we are going to look at the shape bounded between the graphs of y equals x squared and y equals x. All right, so let's remember what these look like. The graph of y equals x is just a line here. And the graph of y equals x squared is a parabola, which goes under and then meets up at the point 1, 1. So there's 1, 1. So we are looking at the area in between these two graphs right here. This little bean pod shape. And we're going to try to find the coordinates of the centroid here. So the first thing to do excuse me, sorry about that. The first thing to do is I'm going to find A, the actual area of this graph here. So A, the actual area within the two graphs here, is going to be the integral from 0 to 1, so far left side to far right side, of the upper curve minus the lower curve. So that's going to be y equals x minus y equals x squared. So we're going to take x minus x squared dx here. Okay, so taking this integral here, we know how to do this. Use the power rule. We're going to have x squared over 2 minus x cubed over 3 evaluated between 0 and 1. If we evaluate at 0, we're going to have 0 minus 0 is 0, so that one doesn't contribute. If we evaluate at 1, we're going to have 1/2 minus 1/3, which is equal to 1/6. So the area that's actually going into each of these expressions is going to be 1/6. All right. So now, let's calculate x bar first. X bar is going to now be equal to 1 over 1/6 times the integral from a to b, that's now going to be from 0 to 1, of x times the quantity f of x minus g of x. So again, that's going to be upper minus lower, x minus x squared dx. So now we can simplify. 1 over 1/6 is the same thing as just 6. So we have 6 out front. And then we have the integral from 0 to 1 of x squared minus x cubed dx. So take the antiderivative in each of these cases. We're going to get 6 times x cubed over 3 minus x to the 4th over 4 evaluated between 0 and 1. And once again, when we evaluate at 0, we're going to just have 0 minus 0, so that one doesn't contribute here. But when we evaluated x equals 1, we're going to have 1/3 minus 1/4. That's going to come out to be exactly 1/12 when we're done. So we're going to have 6 times 1/12 comes out to be exactly 1/2. So this 1/2 is going to be the x-coordinate of the center of mass here. It's going to be exactly halfway between 0 and 1. So there we go. And this makes some sense, right? Because if you split this down, the center here, you should actually notice that there's some symmetry on the right and left sides in this case. I guess not symmetry exactly. I don't know, maybe it's not so obvious looking at it, but this is what the math points us to. We do, in fact, get exactly 1/2 for the x bar value. Okay, so now that we have x bar is equal to 1/2, I'm going to do some erasing, and we're going to find y bar, the center of mass y coordinate. Okay, so y bar now, again, is equal to 1 over a on the outside. That's going to be just 6 times our integral from 0 to 1 of 1/2 times f of x, the quantity squared. That's going to be my upper function squared, minus my lower function squared, x squared squared. dx. Okay, simplifying, we can factor out the 1/2. 6 times 1/2 is 3. So we have 3 times the integral from 0 to 1 of x squared minus x to the 4th. So take the antiderivative in each case. We're going to have 3 times x cubed over 3 minus x to the 5th over 5. There we go, evaluated from 0 to 1. For the third time, when we evaluate at 0, nothing's going to happen, right? We'll have 0 minus 0 is 0. So the only parts that actually matter are when x is equal to 1 here. We're going to have 1/3 minus 1/5 inside of here. That's going to be 2/15 when we multiply it all out. So we're going to have, 2/15 times 3 will be the same thing as 2/5. Yes, I was correct. So 2/5 or 0.4. So the y coordinate for the center of mass here is going to be 0.4, which comes out to around there. And so this coordinate right here is our center of mass. You can see there should be about half the mass above and half the mass below, half the mass to the left and half the mass to the right. So there you got it. The center of mass of a of a region, which is not just a region under a graph. It's the region between two graphs. This is our method of calculation here. All right. In the last video, we're going to introduce what's called the theorem of Pappus, which is a quick result related to centroids, and then we're going to finish for the section.